SwayamPrabha. Digital India. Educated India.
Welcome to today's lecture. So far we discussed about the sedimentary process as a ore forming process, taking the chemogenic sedimentary process into consideration. We had a brief overview of the banded iron formation and the associated manganese deposits older in old cratonic blocks, in old deposits almost in the late Archean to almost late Proterozoic time, and we also got ourselves reminded that as far as the iron deposits are concerned, there are no modern analog available, or these deposits never formed after 800 million years or so. There has never been any such concentration of iron deposits comparable to what we see them in the Precambrian. So, the origin of these deposits remain pretty conjectural in many of the cases. So, now we move on to the process which is will be again a process which will be exogenic, driven by the energy being provided by the sun, but they are pretty efficient process as Earth's own beneficiation mechanism. And let us first discuss the deposits which result from the process, which we broadly call as mechanical concentration. Mechanical concentration will be essentially means the surface operating process by agents such as water, air. The water will be either could be a river, that is a fluvial cycle, or could be the sea waves where it is, or it could be air. So, I will be restricting myself for this discussion to the fluvial cycle and the river being the main agent of this process, resulting in the deposits which are mechanical concentration deposits and which are broadly known as the placer deposits. We can see the diagram. This is a cartoon where I have just drawn, just for your understanding. Let's take for example, here is an exposed rock, is present as a hill somewhere in the continent, in the continental part, and let us say the way it is shown, it is a granite, and this granite shown by these black circles, a little exaggerated in their size, they are representing some mineral. Let us say it could be a cassiterite like a tin oxide, or could be a uraninite UO2, or could be free metal like gold, which is there in this rock mass, and the rest of the constituent of the rock are the normal silicates like quartz, feldspar, mica, etc. And this particular mass of hill is being subjected to active weathering. Maybe it could be the weathering which causes just the mechanical weathering, which could be just maybe depositing some sediments on the foothill, where we call them as the alluvial sediments, which just very close proximity to the hill on the foothill region. And also this area is being dissected by, this is indicating a river, and in this region it is indicating the infant stage or the juvenile stage of the river, where there is active transportation, hardly any deposition is taking place, and this represents the mature stage of the river, where it is meandering, and this is a very common knowledge in any textbook depicting physical process, physical geology, where the river cycle is shown, and these are all we know that the velocity of the water is in this kind of meanders is maximum on the outer lobe and then the inner one, which is the, so they do deposit situations like this, which are the point bar deposits. And here what will happen is that these minerals like cassiterite, which is just an O2, or any other like a uraninite, or could be gold, which will have at least 3 or 4 times or more than that the specific gravity of the normal silicate minerals over here. And these areas where these sediments are deposited will be enriched with respect to the materials which are higher in specific gravity, and that's how we get them as the deposits, which we call them as the placers, which are the alluvial placers. So what we get here is essentially, it's not that we get the particular mineral of interest as a pure form, all lying like to be taken out, but this kind of situations, or when we see them, it's a very, very simple situation which has been depicted here. It's actually not just that mineral of interest, it is also mixed up with the other detrital particles of the common rock like a quartz or any other mineral, and that's how, but only that this mineral of interest, which is of a higher specific gravity, has a higher concentration in this region in the placer deposit. So we need to, it would possibly be worthwhile to understand what exactly happens. That means we would essentially be looking into the mechanism of this, the hydrodynamic condition in which the detrital particle will be transported by in a river channel, and what the conditions would be that will result in a deposition of these particles. And then we will see some examples, some classic examples of such kind of placers which is resulting from this fluvial process. So here there are some very fundamental illustrations which are here. This is how is the flow can be described. The flow velocity increases as we move up in the in the z direction, and the flow could be either be a laminar flow or turbulent flow, depending on a parameter which is a Reynolds number, which is given by, I am not getting into much of the derivation of this because this is out of the scope of this discussion, but they depend on very fundamental parameter like fluid velocity, the length, the fluid density, and the viscosity of the fluid. And this is a situation, so the situation could be anything between a turbulent and laminar, where if we look at this section of the river channel, we see that this is the bed of the river, and this is the immediate layer which is adjoining the bed is the viscous sublayer, where there is a drag that is being experienced by the water, and there is a threshold shear stress, and this is the region in which the flow will be different than here. The flow is basically the turbulent generation layer, and as we move up, the turbulence decreases and approaches towards something like a, if not exactly laminar, but much less of a turbulence. And this is the outer core region, and this is the, so most of the transportation of the river system will be taking place where as we go up in the river section, it will be the particle sizes will be finer and finer, they will be in suspension, we will just see them here. The process can be visualized in this way. They are the closest to the river bed. These are the coarser particle which are transported by series of jumps or the saltation kind of process, where they could be sliding, they could be rolling, and because we are primarily interested in looking at that we have different minerals of different sizes, shapes, specific gravity, and how and what conditions we can get them concentrated or deposited in a way that will lead to, or we can see that what basically happens when this kind of process takes place and how the deposition takes place. So this is a very fundamental diagram. This Joule-Storm curve is basically shows how sedimentary processes can be assessed in terms of hydrodynamic flow. So this, on the x-axis you have the sediment size going from clay to boulder size, as you know the size ranges of them, this is about less than 0.001 of a millimeter to the clay size and going to 1000 millimeter to the boulder size, and we have the intermediate sizes. So we are seeing three regions dominantly. This region which is marked by pink is a dominant domain of deposition, and this deposition actually is depending on the increasing particle size, and so even higher the particle size here, they can even be deposited even the velocity is high, and it's pretty well understandable. This is the erosion and transport. This is the critical value for the critical curve for this critical conditions for the deposition here, and this is the dominantly the transportation in suspension. So this is the this region actually shows the transport as a bed load. This is it. So this corresponds to the vertical section. Here is the region in which the particle size is less, so they will be mostly going as suspension. Here the particle size are larger, they will be going as bed load, and this is the critical erosion velocity curve. So this gives us some fundamental idea about the control that is exerted by the flow conditions. So what essentially we would be looking at is the sorting mechanism, that how, because sometimes we will see that in a placer deposit of say gold, we see quartz, gold, and maybe sometimes some other mineral being deposited or being deposited together, constituting the placer deposit, and we know that they vary in their specific gravity, their sizes. Then we will see whether how under the what conditions. So essentially there are four such mechanisms for the deposition or the hydraulic sorting mechanism. They are relevant to placer formation. We could either have a free or hindered settling of the grains. We could have entrainment of grains, means the grain will be move from its rest position. It should start moving from a granular bed load by flowing water, shearing of grains in a moving fluidized bed, or differential transport. These could be the four possible mechanisms, and let's see the first one. Here is the case of settling, for which we can take help of very simple relations that is there, which is a Stokesian relationship, which involves the acceleration due to gravity, the particle diameter, the difference in the density between the particle and the fluid. So that's written by del P and the del F, and rho is the viscosity. So this illustration here, what it actually showing is something which is called a hydraulic equivalence, where quartz of a larger diameter, pyrite of an intermediate diameter, and gold of the smallest diameter, where the diameter is 0.5 here, it's 1, it's 16, and their density here, its quartz is 2, the pyrite is 5, and the gold is 17, and there we find that this velocity of quartz is Vq and the velocity of pyrite is Vp and Vg. It might, if allowed a condition of laminar flow, or allowed as a condition of unhindered settling, then these three possibly would settle with the same settling velocity, and would possibly explain that why these three would be together in any placer deposit. And here we see that the settling velocity is being expressed as a square relationship with the diameter, but then this we know that this is far from what exactly happens in nature. There are three reasons. Firstly, that the flow is not laminar, and the particles are not necessarily sphere. The particles size may be too large or may be too small. Say for example a biotite and a quartz, large particles also have larger frictional drag, which is not being taken into consideration in the Stokesian settling velocity, and it could be turbulent condition. So looking at this, so more realistic relationship which was given, which again we have not been deriving here, but we could just see here that instead of having a square relationship with D, actually it is having a square root relationship, where CD is the coefficient of drag and is equal to 24 times the Reynolds number. So that possibly would more correspond to a situation where these kind of basic assumptions are violated, that the particle and here the situation is that when the the particle density is more, then there will be interference of interparticular interferences, and simple laws would not hold, simple square laws will not hold, and the more realistic velocity would be given by a square root relationship rather than a square relationship. So here, so that is all about the settling. So now the other mechanism is the entrainment. That means the here a parameter which is called a shield parameter is defined as the critical shear stress required to initiate the movement. So that is the shield parameter represented as theta. The g is the acceleration due to gravity, and the d is the particle diameter, and the two terms, the del p and the del f, as defined before. There is the density of the particle and the density of the medium, this water. So if we look at this, the diagram on the left explains us what exactly happens. So if we take the shield parameter, then it is on a logarithmic scale here, 10 to the power minus 2 to minus 1 and 0, and we do have a, can be defined that the region over here the particle will be entrained, and if the shear, that the shield parameter which is coming out of the expression that we showed just before is falling, is lower in its value, then there will be no movement. It's essentially we have to see that at what condition a particle has to move from its position of rest, will be taken by the transporting medium, and this shows the threshold conditions between the entrainment and the non-movement. So this is essentially is a parameter, that's p and d. So here this p by d is 0, and the p by d value 0.2, 0.4. So the more the p, the greater are the chances of its entrainment. So that's how it will go to lower and lower values of threshold of the shield parameter. And then this diagram shows that this is the critical shear, the shear stress that's required for the entrainment, and it very much depends on the density of the particle. So when gold is around 19 and ilmenite is 5, quartz is 2.5, and we see that the critical shear stress is more, and this is the diameter. More is the diameter, more is the shear stress, and more is the density, more is the shear stress that is required to get the particle entrained in any flow condition. And then the shear sorting is just to impress upon the fact that sometimes we do see, say if we start with say for example in this, as the diagram has been shown here. So the sorting is essentially is a function of the two different densities, that's where were defined before, the lighter particle and the heavier particle. So the shear sorting is always will be in terms of the relative values of the densities of the particles. So here is the lighter, L is for lighter and H is for heavy. So there are two grains of different densities coming to rest in the same horizon would have the relative sizes d. So d of the heavy particle and the d of the lighter particle will be related in this expression, where the dh and dl are the diameters of the heavy and the light particles, and the other two parameters, the del parameters, which we have defined before. So what is interesting to see here is that suppose we start with a material where it's constituted of quartz and magnetite. Quartz and magnetite are of different contrasting density, and suppose we start with a material where quartz and magnetite are in a proportion of 90:10. So if we bring out such conditions here, the relative height of the granular of this bed in any bed where they are being transported, if you see the height here, so there will be a zone in which at a particular height within this column, there will be a zone in which there will be an increase in the magnetite proportion. So as it's shown here, the magnetite concentration in percentage, this line represents the original percentage of 10% of magnetite. We can have in the sediment even as high as exactly double of what it was originally by this process of this shear sorting. And then the transport sorting, that is the last mechanism for the hydraulic sorting mechanisms. the differential transport rates that exist during movement of particles in a flowing fluid medium, the suspension setting and bed load movement, this concentration, this is again here the heavy and the liquid particles are taken into consideration if they are coexisting at any point in the channel flow. Here the Ca is a reference concentration, and it can be shown by this kind of a relationship where H is for the heavy and the L is for the light particle, and the V is for the velocity of the heavy particle and the velocity of the light particle. So this predicts that particles in a turbulent flowing channel will be sorted vertically along their settling velocities, according to the settling velocities, which in turn according to the Stokes law are determined by the relative sizes and densities. So here it says when Stokes law only talks about their relative sizes, it also this according to this transport sorting, the velocities at which these particles are moving is also a parameter which decides whether there will be deposition and there will be sorting. So now we can see how this helps, or how this kind of thing we can correlate to the process of placer formation. It requires a little bit of a more of finer details on exactly the process of sedimentation that is taking place when exactly a cross bedding is forming with the four-set laminae, and where the in a flowing water system. So that requires a little bit more of expertise and more of understanding on the details of a sedimentation process, which I am not going to discuss in detail here. And but the fact is that these processes are manifest in starting from very small scale to very large scale. Means if we are examining a particular sedimentary horizon with the sedimentary features that we see, the cross beddings, this where we know that these things have come up because of the velocity differences in minor scales and the transporting characteristics. So we should be able to see situations in which the particle enrichment and the sorting of these particles and fraction of the heavier particles that will be there in any particular domain can be correlated, and we see that it comes. So whenever we look at a placer deposit, we should be able to dissect it through to look that how such small domains of the local scale or very micro scale enrichment have given rise to such huge accumulations in the form of a big placer deposit. And what we have in front of us here is the famous Witwatersrand Basin paleoplacer gold deposit in South Africa. Is one of the major paleo deposit. It's an old deposit. It's in the Archean. It has given a good amount of gold production over the past time. And this diagram, which is taken from the book of John Ridley, is the plan of the Witwatersrand Basin. So this basin, this part which is the Witwatersrand Basin with the central Witwatersrand group, is about 60,000 kilometers square. Possibly it's difficult to find any present day analog of such kind of huge fluvial system in operation. Now what we see here is that this is the what is shown here, those small places here marked like this, these are the individual deposits, the gold fields. There are about 6 or 7 such gold fields in this entire basin, and this basin is surrounded by, there are some granite domes, and the black part is the greenstone belts, which we will be discussing what they are actually as producers of gold when we come to the topics on hydrothermal deposits. But for the time being, it will be worthwhile to note that this basin, which has been one of the major resources for gold and uranium both, is in proximity to some such occurrences of gold deposits in the close vicinity, and this basin has very rich pockets or these deposits of gold, total about some 6 or 7 in this entire basin. Now, what we could possibly look at here is the column which shows the Witwatersrand group of rocks, the West Rand and the Central Rand. They do contain the gold accumulations in the form of what is basically written as these reefs. Generally they are termed as reefs. They are essentially conglomerate horizons where there has been enrichment of gold, uranium with some amount of pyrite, and intervening shales which are given here as in black color. And these are the horizons which are shown so there are many reefs. Here is one, this one is the dashed black line, 1, 2, 3, 4, and these reefs, these conglomerate horizons containing gold, occurs about 3 kilometers above the base of the basin. So this is the basement which is shown here, and we only concentrate on the group of this Witwatersrand group of rock, because the later one, even you see the famous Rediford dome, which is essentially a meteor, they say impact crater. And what is very interesting here in the Witwatersrand is that those 6 or 7 those 7 places where we saw the gold deposits accumulation, they can be roughly correlatable. The reefs are very much correlatable in a basin scale, as has been shown here. These are the reefs, the gold bearing reefs, which can be very well correlated. And what is shown in terms of the pie circles here with part blackened is essentially showing the proportion of gold field production. So you could see that almost all, just about one, almost all are very extensively gold producing horizons here. And so the gold, most of the gold has come from the stratigraphically lowest reefs, which are here, and this is the main reef, this is the south reef. These are the stratigraphically lowest reefs, and the upper reefs are not that very gold containing, which can be shown here. Like here, very little of gold is coming, and but the lower ones give the maximum amount of gold. And as I mentioned, that they are not just pure gold, they contain gold and uranium with pyrite and quartz. The conglomerate horizons are essentially from the bodies of quartz which must have been exposed anywhere in the nearby areas that we show. So while discussing about the manifestation of the mechanisms, sorting mechanisms that we just saw, from the very small scale to large scales, this diagram shows that these are the scours where we get dominantly the sand deposits, and these are the intervening conglomerate, which are essentially the gold bearing reefs. And we see that there are series of such, and these conglomerate, these gold bearing reefs, they are occupying exactly a position just above a non-conformity. And so that means, which indicates that there has been many series of such reworking of the several stages of such erosion and deposition in this basin that has gone in, and that might have possibly worked in getting the gold further and further enriched to give rise to this rich gold occurrences, where the gold could go to even the reefs are generally, what we see here is about 5 to 2 meter, 5 centimeter to even 2 meter in their thickness, and the grade decreases down deep, and the beds are generally conglomerate or pebbly sandstone. And what is observed here is the thinner the bands are, the richer they are in gold, and this gives a rough idea about the relative uranium and gold concentrations in these reefs. The grey part shown by uranium and the lighter part shown by gold. So where you could see that the uranium and gold proportions vary, which can be shown here, and how the processes are manifest in local scales. Here we could see that these are representing the anastomosing braided pattern of the basin, and the slope is actually from north to south, and is very well correlated. If you look at here, this the uranium and the uranium by gold ratio. So, in this diagram we can see that these represent the area where there are better gold mineralization, and the areas here we see the greater uranium mineralization. If we could plot them together, it would look as if from north to south the northern part is more rich in gold and the southern part is more rich in uranium, and actually it shows that I mean there has been some efficient sorting mechanism that has taken place. And this is the this is an interesting situation, the interpretation of the Wheatwater-Saline basin, which is interpreted to be a result of some 5 or 6 major rivers, and this particular sequence of the sedimentation almost goes to 6 to 7 kilometers in the thickness, and one would wonder that how such thick sedimentation took place, and so that is why it was visualized that there has been progressive uplift of the provenance area during the formation of this basin. This provenance could be as distant as could be the Limpopo belt, which is about 250-300 kilometers, and this diagram gives a very good idea. So, this is the vertical section, and this is the Wheatwater-Saline basin, which this is a picture that depicts the situation resulting from the work of 5 or 6 major rivers during that time, and we still do not see any such present day comparable situations in which such large river systems are at work, and whether any such kind of a present day gold deposit forming process is actually operating or not. So, thank you very much. We will continue with the sedimentary process in the next class. Thank you.